Someone asked me a question about why there is separatrix. Why this configuration of pulsar magnetosphere has to have a current sheet at all. And the basic reason why there should be current sheet, why the system relaxes to that state, is the fact that some field lines are open and some field lines are closed. So these red field lines are open just because the plasma on those field lines cannot co-rotate. The field lines that cross the light cylinder cannot possibly co-rotate with the star, because that would imply this plasma moving with the speed of higher than the speed of light, faster than the speed of light. So that's why plasma, instead of co-rotating on those field lines that cross the light cylinder, instead of co-rotating, plasma just is launched away from the star and it flies away. And it carries field lines with it, so the field lines become open. So the field lines that cross the light cylinder are open. By contrast, field lines that are inside the light cylinder, they remain closed. And there is no toroidal component, there is no B-phi, azimuthal component of the magnetic field in this closed zone, simply because the field line is attached with both ends to the star, and it just moves around the star like that. There is no reason for generating a twist, right? So you generate B-phi only if one end of the field line is moving with different speed than the other end. Then you can stretch it and you generate the phi component of the field. So that's not happening in the closed zone. And these field lines remain with zero B-phi, no electric current. It's like dead zone, essentially, no activity there. The separatrix is the topological feature of the system. It's the boundary between open and closed field lines, essentially. And so at this boundary, the magnetic field, the toroidal magnetic field, as you cross this boundary, disappears. So there is a jump in B-phi from zero in the closed zone to non-zero value in the open zone. The open field lines are, of course, twisted. There is B-phi because these field lines, you can think about it this way. So the field lines go beyond the light cylinder, and the star is rotating a bit, tries to rotate a bit faster, and it generates this twist. That's why the field lines turn around and they form this helical structure. So there is B-phi, there is poloidal current, and there is B-phi on the open field lines. So the current sheet is there simply because there is a jump of B-phi. In the closed zone, no B-phi. In the open zone, strong B-phi. And this current sheet screens, it's just it's the boundary between the two regions. It screens this toroidal field. So the system has to, the system is very smart in the sense that it finds a way to actually let the electromagnetic configuration to relax to that state through creation of electron-positron pairs. So it generates this current, and pairs are created along this current sheet, and you have this singularities, basically, that is the boundary between the two zones. Okay. Now let me move on. So I talked about accretion a little bit. The next energy source is magnetic field, which I will discuss separately. So this slide simply shows that, mentions the characteristic magnetic energy that you can have stored in the star if it has a very strong, but it turns out realistic magnetic field of 10 to the 16th Gauss. So you can have energy exceeding 10 to the 49 erg. That's a huge energy. If you find a way to convert it to heat or to radiation, you can produce a very bright star. Okay? So that's what we call magnetars, and I'll talk about them separately. Well, I'll briefly mention the energy source 4 that was mentioned in the beginning. Remember, that's the orbital in spiral. Samaya will talk in much more detail about that. And Francois talked about physics of neutron-star merger. So I just wanted to mention that huge energy is released in this case, and you have gravitational waves that you anticipate to detect from this merger, and they have been detected by now. first indirectly by measuring how this famous House-Taylor double pulsar neutron star binary, how its orbital spin period changes with time. We observe how the binary system shrinks with the rate consistent with prediction of general relativity. What you see here is the evolution of the orbital rotation as a function of time. So the binary shrinks and begins to rotate faster and faster as a function of time with exactly along the curve that is predicted by general relativity. So that was the Nobel Prize in 1993. So it was clear that gravitational waves are there, but now they are detected directly by LIGO and Virgo. And of course, the gamma ray burst was detected, and Samay, I'm sure, will tell you more about that. I'll skip this part, how neutron stars merge. So there are gamma ray bursts accompanying mergers. We know now that it was a weak burst, but still interesting. It belongs to the class of short gamma ray bursts. Samay.
You can expand on the GRB stuff.
Okay, good. So, okay, so let me then say this, that when you have a merger, you normally have a debris disk, which Francois, I'm sure, talked about. And this debris disk launches a jet, collimated flow, strongly magnetized, and ultra-relativistic. This we know from observations that this outflow is ultra-relativistic just because we observe gamma rays on very short time scale. Typical duration of a burst is like comparable to a second. Observationally, so it was suspected for a long time that these kind of events, for which there was a rough estimate of the rate, how many of them happen per unit time in the universe. And the general idea was that observe two classes of GRBs, so-called short gamma ray burst and long gamma ray burst, are produced by two different mechanisms. So one is associated with neutron star merger, and the other one is associated with collapse of a massive star, so-called collapsar scenario. And well, what this diagram on the right at the bottom shows is each dot there is a burst. You see many bursts there, and they're shown on the plane of duration. T90 is just a measure of duration, is the time window during which 90% of the burst is received. Just this duration, you remove the first, you remove basically 10% of the burst, and the rest time window is the duration. And the vertical axis is the position of the spectral peak. As you can see, GRB spectra normally peak around 1 MeV, 1000 keV. And so on this diagram, you see kind of two clouds. Well, you are guided by the color, but it's statistically very significant. So there is this pink, orange color and green color. I mean, it's quite clear that the long burst, so green color here is quite clear. You can see congregation of these dots around 100, 200 keV peak and durations of seconds, 3 to 10 seconds to 100 seconds. And the orange cloud is the short bursts, which are a little harder. They normally peak closer to 1 MeV, photon energy, and the typical duration is less than around 1 second. So the fact that you see this bimodality in the distribution of bursts on this plane was suggestive that there are two, just pure phenomenological argument, two different classes. And the idea, which was around for a long time, is that short gamma ray bursts are produced by neutron star mergers. And it was consistent with the position of these bursts on the sky. They're usually offset from their host galaxies, and therefore it's consistent with the system that is very old. And two merging neutron stars are normally a very old system because it takes a long time for a neutron binary to merge. So this binary was ejected from the galaxy with some speed, and it lived for a long time. It traveled some distance, and then it merged. Then we see a gamma ray burst which is somewhat offset from the galaxy. That's the effect that's kind of observed in the short gamma ray burst population. Unlike the longer gamma ray bursts, which are normally associated with star formation regions in galaxies. And that's consistent with the young star collapsing, with this collapsar scenario. Okay, so that's That was the expectation that it should be gamma burst. And there was a third expectation that I'm sure has been discussed. Somehow you'll probably talk about it, right? The kilonova stuff and our process.
Yeah, Francois did it.
And Francois did it.
Yeah.
I have just one slide. So I think you've seen, guys, that, right? So you don't. There is our process that generates interesting elements like gold, uranium. And R means rapid. And rapid means that capture reactions proceed faster than beta decay. So neutrons are captured faster into nuclei than they decay. Okay, and it's a way to generate big nuclei, which are neutron rich, and then they decay and produce the chemical composition, which we call R process composition. So they're responsible for heavy part of the periodic table, and neutron star mergers are natural sites for the R process, because things are happening. First of all, you have many free neutrons. It's a compact object, highly neutronized. You eject a lot of neutrons, and everything happens fast, quickly, on short time scales. So in these outflows, and detailed calculations have been done, like starting from the 70s. Basically, what you see in the models is that once you let this cloud expand quickly, there will be some nuclear composition freeze out, which is consistent with the observed R process part of the abundances that we see for those elements that we call R process elements. Right, and in addition to that, you also expect not just production of these elements, but also expect optical light, optical infrared light from this cloud expanding from the merger, precisely because of decay of these neutron-rich elements. They're radioactive, and just like normal supernova, but different elements, they decay and deposit heat into the cloud. Otherwise, the cloud would become completely dark. So if you have a cloud expanding from a compact object, even if it's initially very hot and luminous, its size is small, so you don't see much luminosity. And by the time it expands to a big sphere, when you hope it will become a bright source, if you don't have energy input, it would become completely dark because of adiabatic cooling. Right? It has used its heat, its pressure, and its internal energy to expand. It's converted its internal energy into bulk kinetic energy. And so it would be dark if not the nuclear decay reactions that supply heat at later times and light up this cloud. And that's why this cloud emits optical radiation. That's what we call kilonova, which has been nicely observed in this famous event of gravitational wave detection, accompanying this gravitational wave detection. And from that, and comparing with the predictions, you can see that how much gold and everything is produced. There was a big kind of celebration, which was nice. That a particularly nice aspect that it was almost exactly 50 years after the discovery of pulsars. So that, of course, may be the biggest discovery in neutron star physics, maybe except one another big thing that happened, I'll talk about this later, is fast radio bursts that may be associated with neutron stars. So pulsars discovered in 1967, FRB is discovered like 10 years ago, and now we have neutron star merger. Okay, that's the optical light that is consistent. The squares are the observed, the data, and the red is the prediction, and the amount of different elements you can see. 100 Earth masses of gold, pretty nice. Platinum, uranium, impressive. 50 solar masses, Earth masses. Okay, so here is my summary of this general overview of neutron star activities. Four mechanisms that can make a neutron star luminous. Rotational energy. If you think of it, actually it's not rotation going directly into photons. If you think of it as a physicist, what actually is happening is that rotation is first transformed into the Poynting flux, and then part of this Poynting flux is dissipated in the magnetosphere. Right? So when you drag the field lines, you create some kind of E cross B flux, and it would leave the star in this idealized model of vacuum rotator or force-free model with no dissipation, and it would be completely dark object. It is the dissipation of Poynting flux that happens on the way due to these features, the Y point, this current sheet, and the necessary electron position discharge, this kind of continual lightning that operates there. That's why you see this as a bright source. So it's still kind of dissipation of magnetic energy, basically, that is happening around pulses. But the ultimate energy source there is rotation. Well, the very ultimate energy source, of course, is gravitational, because the rotational energy came from the collapse. So from the beginning, it was gravitational energy going to kinetic energy, spinning up the star. Then it transforms into Poynting flux, and then Poynting flux dissipates. Then accretion, magnetar activity, well, I'll begin to discuss it now, and the merger. And then you see what I think are most exciting future developments in this field, understanding the details of electric gap, and in particular how we produce coherent radio waves. That's still not understood. We have the tool, we have these particle and cell simulations that presumably should give you the complete information about what's happening on the plasma scales, because they resolve all the plasma scales. They resolve the debye scale, the skin depth of the plasma. They follow all the collective processes. And so if you have bunches of charges, like antenna type of mission, they should show up in these simulations. But it has not been analyzed enough yet, and it's a very young field now, this numerical simulation, just a few years old, and that's the future. I think we'll understand very soon the radio mechanism. The death line, so-called, of pulses need to be understood better. That's the line, if you like, in the speed of rotation below which you stop producing pairs and the pulsar does not operate anymore, which is observed in the data also. Some pulses which rotate too slowly, you can only have a pulsar when it spins rapidly enough. In magnetars, I'll talk separately, and in merger, of course, we hope to see more events, basically. Gravitational waves, GRB mechanism associated. These are off-axis GRBs, what we call, because we look at the merger something like 20, 30 degrees. Unlike canonical GRBs, where we think we look almost on axis, and because of the beaming, in that case, the source is much, much brighter, and so you can see that from much larger distances, from cosmological distances, from very distant galaxies. So these are not quite canonical GRBs, but we think that probably maybe normal GRB, but we just look a little bit off axis, and it's interesting to have more statistics, to see more of this, to understand the physics of the merger event and expansion of that cloud that generate the emission from different angles. And our process in detail, of course. Was it normal yield of all these elements, or it varies from merger to merger? And what are the properties of the merging neutron stars? What are the typical masses, mass ratios, spins of neutron stars? You can study all that using mergers. All right. So now, let me begin to discuss in more detail magnetars, which is a complicated topic. But my goal is to give you some sense of what is being done in this field, which is interesting. There is lots of physics in this field. Now, the short definition of magnetar is, you would say, it's a magnetically powered neutron star. So that's a neutron star which is bright because magnetic energy is somehow dissipated there and converts to photons. Meaning like removing even internal magnetic field. This is not happening in normal pulses where we think magnetic field is frozen and you only tap into the rotational energy. Here we're going to tap into the magnetic energy stored inside the star. Well, here is my plan. Hopefully I can cover it, not today, not all of it, but so I'll start with observed behavior, then talk about physics of dissipation inside magnetars, and then physics of magnetar activity, electron position discharge, and some observed phenomena, giant flares in particular. And then I'll talk about FRBs, the emerging connection between magnetars and fast radio bursts. This is a new discovery in radio astronomy, the biggest one after the discovery of pulsars. First, to give you some sense of where magnetars are on the map, on the one-dimensional map, where the coordinate is the magnetic field. So you can see the Earth have 0.6 Gauss approximately, common magnet something like 100 Gauss, 10 to the minus 2 Tesla, right? Sunspots up to kilogauss. The average field of the sun is roughly 1 Gauss. Magnetized white dwarfs, strongly magnetized, 10 to the 8th Gauss. Okay, very frequently less magnetized, but go to 10 to the 8th. Now, radial pulsars, these are neutron stars, already make big leap to 10 to the 12 or 10 to the 13 Gauss. And the field could easily be created just by amplifying the field that was this 1 Gauss field that was initially in the progenitor star, simply by compressing it and conserving the magnetic flux. You will reach this kind of fields easily, 10 to the 12 Gauss. Well, you can estimate it by yourself, right? So what's the size of the sun if you take off a star? Do you remember what's the size of the sun? Roughly, order of magnitude. The size of the 10 to the 11th, yeah, 10 to 11 centimeters. So this is 10 to the 5 times bigger than the neutron star, right? Which is 10 to the 6th, 10 kilometers. So when you collapse by 10 to the 5, the area goes up by 10 orders of magnitude. So if you start with field like 100 Gauss, you end up with field of 10 to the 12 Gauss. That's simple. B times R squared, the magnetic flux, is conserved in the collapse. But of course, there are additional processes that can amplify field even more. Dynamo processes in particular, because when the neutron star is born, it's very hot, and it's convective actually. The simulations show that. So after the collapse, the neutrinos are initially trapped. The neutrino cooling becomes efficient on time scales of like fraction of a minute, but the star tries to cool down through convection. Okay. So this convection combined with rotation, if rotation is fast enough, generates the so-called dynamo processes, which amplify whatever field was there from the beginning. So it can, in principle, it can amplify the field up to the equipartition. Equipartition meaning that b squared over 8 pi is comparable to the thermal energy of the star or gravitational energy. If you really insist that your magnetic field now is in equipartition with the total binding energy of the star, you would get fields like more than 10 to the 17th Gauss, which some people think might be possible. That becomes interesting also because such strong fields would change the shape of the star. Because magnetic field lines tend to, it's like hoops which have tension that they try to squeeze the star. And so the star changes a little bit its shape. And if it's somewhat inclined to the rotational axis, you will have a mechanism for generating gravitational waves, right? You will have a quadruple moment in mass, and you will generate gravitational waves. So magnetic fields could be responsible for producing gravitational wave emission from rapidly rotating just-born neutron stars. But for that, you really need fields to detect it, like 10 to the 17th Gauss. It's unclear if they reach that value. But who knows? Because, well, now, as I will tell you in a minute, we are pretty sure that fields go up to 10 to the 16th Gauss. About 20 years ago, 25 years ago, fields exceeding 10 to the 13 or 10 to the 14 would be thought of as nonsense, kind of. I mean, it was, some people would speculate, but normal adopted number, okay, strongly magnetized pulsar like crab, still below 10 to the 13 Gauss. But theoretically, if you think of it, why not above 10 to the 13? Why not above 10 to the 14? So it was more like psychological bearing. So who knows? Maybe now we are comfortable with 10 to the 15th, and already beginning to be comfortable with 10 to the 16th. Maybe at some point we'll become comfortable with 10 to the 17th. But so far there is no good observational really reason for that. So okay, so you can see that magnetars on this scale are absolute champions in terms of magnetic field strength. These are the places with absolutely strongest magnetic field in the universe. Okay. This field is interesting also because you can compare it with the characteristic, what they call QED, quantum electrodynamics field, which you can compose from electron mass, speed of light, electric charge, and Planck constant. You see the expression there, m squared c cubed over EH. H is the Planck constant. This combination has a dimension of field, and its value is 4.4 times 10 to the 13 Gauss. So magnetars have field stronger than that. Now, if you had electric field exceeding this value, you would start to create pairs from vacuum. This is what we call, what is called Schwinger field. If you just take vacuum and you generate electric field exceeding this value, in Gauss units, B and E have the same dimension. Then vacuum is filled with virtual electron-positron pairs. And what this electric field would do, it will make these pairs real. And so your vacuum would suddenly explode with electrons and positrons. Magnetic field doesn't do that, because magnetic field only produces a Lorentz force. So if you have a particle, let's say virtual particle, moving that way, magnetic field would only deflect the particle. It would not accelerate it. It cannot give it energy. So it cannot make it real, unlike the electric field. But still, when magnetic field exceeds these values, there are new interesting effects from quantum electrodynamics. One way of thinking about this special value of field, as you see at the bottom right corner, you can rewrite the same definition as H, Planck constant, times the gyro frequency, EB over electron mass C. Okay, so this it's basically a difference between it's the energy difference between two Landau levels, H times EB over MC. And the condition that B is larger than BQED is the same as this quantum energy larger than electron versus mass. So in particular, if you have in this field, if you have a transition, if you put electron in an excited Landau state and let it relax to the ground state, the photon that you will emit in this transition will have energy above MC squared, and it has the potential to convert to electron to a pair because its energy is sufficient to that. Let's say 2 MC squared would be sufficient. So that's actually what is happening in magnetars. When they generate photons of those energy, and these photons immediately convert to pairs. So it's not curvature radiation that I talked about in pulses. It's just these transitions that can do that. Another interesting effect that happens is that photons propagating in vacuum, in the sense that there is no material there, no plasma, but this vacuum has background strong magnetic field of this strength. These photons propagate differently from vacuum without any field. They begin through this magnetic field, they begin to feel the presence of this virtual electron-positron pairs, and that's what they call vacuum polarization effect. And it turns out that photons that propagate, if you think of it of a photon as a classical wave, where electric field and magnetic field and the wave are perpendicular to the k vector, you can imagine two types of photons. If you focus on the electric field, let's say, if this electric field lies in the plane of k photon wave number and magnetic field, I don't have, so there's a magnetic field, so there is a plane KB plane. If electric field is in this plane, that's one mode, and it propagates with one speed due to this polarization effect. If the electric field is perpendicular to the KB plane, it's the other mode. There are two linearly polarized states that propagates with slightly different speeds, slightly different from the speed of light. So it's like a crystal in a way. It's a vacuum acts as a medium which polarizes your radiation. Another funny thing that is happening is that two photons can merge into one, and they can so split inverse reaction. Of course, this is completely forbidden in a vacuum without field, because you would not conserve. If you have a photon, it cannot decay into two photons, right? Because you need to conserve energy and momentum, and there is no way of conserving energy and momentum with this reaction. But if you have background magnetic field, then it can take part of the perpendicular momentum perpendicular to the field and allow this reaction to occur. And this reaction becomes, has a significant rate for this kind of fields exceeding BQED, and for photons with energy comparable and exceeding electron rest mass. Okay, so photons actually do split near those stars. So that's a fascinating laboratory for physics, for physical conditions where there's no way, of course, possibly to do this in the lab. In this table, you can see the laboratory field, the strongest, is roughly 1 million Gauss, and you can do this only for very short time when you do implosion, for example, because normally the devices, lab devices, cannot even handle, cannot confine this kind of fields. They're too strong. The pressure is too big. So you can impulsively, for short time, you can create this ridiculously low field compared to what magnetars have. Okay. Right, so the discovery of magnetars, which were not realized to be magnetars first, they're called soft gamma repeaters. So that happened in the end of 90s. And that happened through the detection of an object, a bizarre object that began to produce short bursts of soft gamma rays. So in addition to the sequence of short bursts, less than 1 second duration, there was also a giant flare, which is shown in this plot, which was really bright and long, which had a tail lasting, well, here it goes to 60 seconds, but we know now it goes to basically 6 minutes. And this tail is clearly, as you can see by eye, is modulated with 8-second period. And that's a signature of a neutron star. So it was clear that we deal with a neutron star, which is rotating with 8-second period, and which can produce a sudden flare, an explosion with tremendous brightness. Tremendous meaning, well, the energy in the tail over these few minutes is about 10 to the 44 ergs. The peak, the first initial peak, its luminosity goes up to 10, well, for this burst it's about 10 to the 45, 10 to the 44, 10 to the 45 ergs per second. Okay, so it's like an AGN, the galactic nucleus. Then we saw two more. In 1998, there was another giant flare, and then in December 2004. The December 2004 one, and they're all the same, by the way. They all have initial peak, which lasts like half second, and then a 6-minute tail, modulated by rotation. So the peak luminosity in the third burst, in the third giant flare that has been detected, and they all came from different objects, 3 different magnetars, reached luminosity of 10 to the 47 ergs per second. Okay, it's a galactic source with luminosity of 10 to the 47 ergs per second. The luminosity of the sun is 10 to the 4 times 10 to the 33. So it's 14 orders of magnitude brighter, just for a fraction of a second, but it's pretty impressive. So of course there was a lot of discussion and noise after this discovery. In parallel, almost the same year, like next year, we see in another paper, and more detection of the similar sources, was the discovery of anomalous X-ray pulses. The term was coined later in the 90s, but anyway, that was the class of X-ray sources, which are also pulsating. I think the first one discovered had a period of 7 seconds. So similar periods, which are very long for a pulse, especially of that age. And by the way, this giant flare, which happened on the 5th of March of 1979, and the accompanying burst, they came from a source associated with the star formation region. So it was clear that it's in the Large Magellanic Cloud, LMC. So it was probably coming from young stellar population. So neutron star, which is not very young. Now this anomalous X-ray pulsar, the other X-ray source discovered in our galaxy, actually was sitting in supernova remnant. And you know, once you see supernova remnant, you know the age of the object, because you see the expansion of the supernova, you can estimate the age. And as more and more objects of this type were detected, bright in X-rays, slow in rotation, neutron stars of this type, it was clear that we are dealing with a population which is young, kiloyears old. Not like the crab, but the crab is very young pulsar. Most of the pulsars, of course, are much older. The average age would be like a million years, and then it's okay to have a second period. But these guys have multi-second periods, and they're only 1 kiloyear old. So they're very strange. Right. So they remained not understood for a long time. Then there was a speculation in 1992 by Paczynski and Duncan and Thompson that the reason for the activity was the presence of an ultra-strong magnetic field. And it was at the time when everyone thought that fields probably don't go above 10 to the 13 or 10 to the 14. And here you would need fields like 10 to the 15th Gauss. So it was a very brave conjecture, completely speculative. There was no observational confirmation, really. But the basic idea was, well, wait a second, we don't have any source of energy for these objects. Really, if you look, there is no sign of accretion, for example, there. And what else could it be? And they conjectured that it could be the decay of magnetic field. All right, then in 1998, there was beautiful confirmation of first one object, and then this plot, of course, is done much later when we see much more. When the magnetic field was measured, and it did turn out to be comparable to 10 to the 15th Gauss. So the way you measure magnetic fields of neutron stars is that you study their spin period and see how it changes with time. So I talked about rotationally powered pulses, right? And you remember that formula, omega to the 4th times mu squared divided by c cubed. All right? So it tells you that the spin down rate, which reflects the energy loss rate, that formula, is sensitive to omega, and it also, of course, reflected by p dot, or omega dot, the rate of change of period. And so if you just use that formula, turn it around and express mu, the magnetic moment, or the surface magnetic field, magnetic moment is basically a radius cubed times b, times the field, right? So if you express from that formula the magnetic field, that would be the formula at the bottom, just tells you what this field should be from measured p and p dot. And that's the main kind of formula that observers use, and it's the main plane where all pulses live. The plane of p period and p dot, time derivative of period. So you can see many pulses with black dots on this plot, and there are two lines, so lines of constant b. Okay, when you fix b in this formula, you have a relation between p and p dot. This with this relation is shown by the two lines for two different fields. So the red line is the QED field. No, sorry, the dashed line is the QED field, and the red line is kind of lower field. And the stars are this magnetar population, soft gamma repeaters, and anomalous X-ray pulses. And you can see they're all above that line, and they all have super QED field. Now, you're only sensitive, when you use this formula, you are only sensitive to the dipole component of the magnetic field, right? So if you have, if the neutron star has a more complicated magnetic field, quadrupole, something, if you expand the multipoles at large distances from the star, let's say the light cylinder, the field will be dominated by the dipole component. There is no monopole, so the next one will be dipole. And so when you talk about spin-down physics, which is tied to the light cylinder, you would only be sensitive to the dipole component. So they can be easily, and we think there is much stronger field near the star and inside the star. In particular, there is a toroidal magnetic field which seems to be hidden inside the neutron star, which is 10 times stronger than the dipole component that we see. Yeah, so soft gamma repeaters, I don't want to talk much longer about this interesting story, but soft gamma repeaters were interesting by themselves for many reasons for a long time. First of all, they were confused with gamma ray bursts initially. So historically, they thought that, well, initially, they thought that after the gamma ray bursts were detected and soft gamma repeaters were detected, they were quite similar, okay, just bursts of gamma rays. And one could think that it's the same population, the same physical phenomenon. But if you look more carefully at them, you find that, and that's what's reflected in their name, that soft gamma repeaters, they repeat, and gamma ray bursts never repeat. The cosmological gamma ray bursts that we'll talk about, like merger gamma ray bursts, Newton star merger. And they have harder spectrum. So these guys repeat, and they have somewhat softer spectrum, meaning that the spectrum peaks not at 1 MeV, but something like tens of 100 keV. Tens of keV. And their sources are detected in our galaxy mostly, and in LMC. Also, this is one example. All right. Just to give you some more information, these are quite amazing, beasts that have interesting life. So they're pulsating, of course, the way you see pulsation in X-rays, and they were discovered in X-rays, and the main energy output is in the X-ray band. So they have pulse profiles, and here you see 6 different objects, anomalous X-ray pulses, which have some different, sometimes simple, and sometimes not so simple pulse profiles. X-ray luminosity is a function of time. So you're looking at an object which is obviously it does not emit isotropically because we see the pulse. As it rotates, it produces this modulated X-ray emission. Another thing that's happening that even in an individual object, its pulse profile changes with time, sometimes dramatically. In particular, if there is a flare or a burst, boom, it goes, it produces a burst. You look at it again, study the pulse profile. Oh my God, it's different. Okay, completely different sometimes. What does it tell you? Well, first of all, it tells you nothing if you don't understand the physics of how these X-rays are produced in the first place. But the simplest model would be, okay, you have a neutron star which radiates like a black body from the surface, and it cannot be uniformly hot, right? So if you see a pulse, you would say, okay, there is a hot spot. So how you would interpret this change in pulse profile? Now the hot spot is a different place. So maybe. It turns out that this simple picture is not quite complete. And in fact, what you see is the photons that come from the magnetosphere itself, which is confirmed by the fact that the spectrum is not really black body. I will show a spectrum in a second. It has a clear structure, but it's different from black body. Okay. This is an example of several bursts, not giant flares, bursts. Okay, there is some rich phenomenology there. So these magnetars produce short bursts, less than 1 second duration. Usually they go multiple bursts. Like here you can see one, then another one. It's a very intermittent process, so they usually cluster it in time. So the object gets activated, like solar activity when you have solar flares, and then there is nothing for a long time. And suddenly it switches on and again begins to produce more and more bursts. And these bursts can have different luminosities, broad range of luminosity, but usually durations are like a fraction of a second of each individual burst. So to summarize their properties, these are objects which are typically 1 to 10 kilo-year in age. They're rotating remarkably slow for their age compared to normal pulses, like Crab have 33 millisecond period. And these guys have periods comparable to 10 seconds, but more than 2 seconds. By the way, another remarkable property is by now we have almost 30 well-confirmed magnetars, and they all have periods in a narrow range between 2 and 12. It's only a factor of 6. Their spin-down power, this mu square omega to the 4th over c cube, is quite small. That's the defining feature. They're slow rotators, that's why. Their spin period, the p is small, even though magnetic field is so strong. Mu squared is big, but omega to the 4th is small, and so their spin-down power is small. Not much energy is fed by, not much power is fed by rotation in their case. And their X-ray luminosity is typically 2 or 3 orders above the rotational spin-down power, so that clearly you have a different source of energy. Okay? Flares go up to 10 to the 47 Earths per second. This is how this population looks in our galaxy. If you look at our galaxy from above, so you can see the spiral arms, you can see many blue dots. These are normal, ordinary pulses, radio pulses, and you see these red dots which show the magnetars. The position along the line of sight is usually not so well measured, so you can see big error bars along the line of sight. Of course, we are sitting, you can see where all these lines points, that's the location of the sun above the center. You can barely see it, but I think it's yellow cross there, 8 kiloparsecs away from the center of the galaxy. So most of them interesting ones. There are a few more. So total, it's 29, I think, well, 30, let's say, 30 magnetars. Their number is much smaller than the total number of Newton stars, 10 to the 8th, the total number, right? We estimated. But in fact, at least every 10th Newton star born in the galaxy is a magnetar, even though their number is only 30 in conference to 10 to that. Can you figure out how it can be consistent? So I'm making a statement here that even though we see 30 magnetars, okay, I'm saying that every 10th or maybe every 5th, or maybe actually, I actually think that maybe every second Newton star born in a supernova is actually a magnetar. Yeah?
Fast spin-down times?
Yes, long, I would a little correct, almost right. It's the short lifetime of the source, right? We only detect it when it is active. That means that its lifetime is short. We know that the ages are only 1 to 10 kiloyears, unlike all other stars that are billion years old. So that's simple, right? So actually, the right way to estimate how many magnetars are produced, you should take their lifetime as an active source that we can detect. And, well, you should take their number, divide by their lifetime, and that's the rate of magnetar production. And it turns out to be a fraction of 1 per century. Okay, so it's a fraction of all supernovae, at least 10%. So it's not an unusual event. It just, and it's a good question, what happens after they switch off as active magnetars? Do they still keep the field? Similar strength 10 to the 15th, like dissipate part of it, and then for some reason the dynamic stalls and it's not active anymore. Should we look for them somewhere nearby? Should we see dormant magnetars? And there is good indication that yes, because we see objects now more and more. Actually, among these 30, like roughly half, are now what they call transient magnetars. These are basically mostly dormant objects which show no activity, can be hardly detected because their luminosities are low, like normal passively cooling neutron star of that age. They are not pulsating. They are, because of their strong field, they are spun down to such ridiculously long periods, so they are not radio pulses. And suddenly they switch on. Something happens, so that at the boundary between active stage and becoming permanently dormant. So there is this hidden population, maybe ocean of Newton stars, of magnetars, which we can barely see, and maybe they keep the magnetic field for a long time. Or maybe it's decaying mostly during this active life, and then we're left with a more normal star, neutron star in the end. All right, so, well, these are two types of activity, just to highlight the complicated phenomenology that emerged in this field. That happens, I mean, not always things are simple, so you have temporal activity, which includes bursts, these short spikes of X-ray emission, flares, which luminosity goes crazy to 10 to the 47, up to 10 to the 47 Earths per second, like a quasar basically, but coming from a 10-kilometer object, okay? Which is weird. I mean, if you think of it, it's a quasar really, luminous, 10 to the 47 Earths per second. Just it doesn't last very long. When the gamma rays come to the ionosphere, atmosphere of Earth, it ionizes it. The flux is so huge, even though it comes maybe from the other side of the galaxy, the flux is enormous. It saturates all the detectors in X-rays except the weakest ones. You can see it only in the reflection from the moon, basically. It's in tremendous flux. Because all the detectors are blind. I mean, when so many gamma rays come to the detector, they saturate the detector. So these are giant flares. They are weaker bursts and shorter bursts. The bursts don't have these long and 6-minute well-modulated tails. Also, there are so-called outbursts, which are more typical for this kind of what I mentioned before, what they call transient magnetars. These are the left figure shows that example. When you have X-ray luminosity which is slow, then at some point, and boom, it goes up for a few years. I don't know if you can see the time scale in this plot is more like, essentially it's a year time scale, unlike minute time scale for the plot on the right. So bursts, second duration, flares, minutes duration, outbursts, months to years, with luminosities like 10 to the 36 beginning and Earths per second, and then decaying. So they show a variety of activity. But in the end, when you just look at how much power has been produced by the object, if you just sum up everything together, it's persistent emission, which is also anomalously high. That's why anomalous X-ray pulses are called anomalous, because people could not understand how come that they don't accrete, but nevertheless they have very bright X-ray sources, right? Unlike other isolated neutron stars. So they have anomalously high persistent luminosity that comes from the surface very often. In many, it's canonical, not transient, but canonical persistent magnetars. Many outbursts. If you sum up all this energy output, you can calculate what is the energy budget of the thing. That is how much Earths have been radiated over the age of the system. And you would come to a number something like 10 to the 48 erg. So if it's magnetic, from that you can estimate the magnetic field that has to reside in the star to supply this energy. And this will be 10 to the 16th Gauss. It's very simple. You know the volume of the star, which is r cube, radius cube. R is 10 to the 6 centimeters, so you take volume 10 to the 18th, right? Then you take 10 to the 48, divide by the volume, then you get energy density, and you equate this energy density to b squared over 8 pi. That's how you find the magnetic field. So volume of the star, which is r cubed, whatever, 4 pi over 3, b squared over 8 pi, is of the order of energy. And the energy, if you use efficiently, like a good fraction of the stored magnetic energy, that's what we need, but this is what we observe, how much energy comes out on the kiloyear timescale from these objects. We know the volume of a neutron star. That's how we find that B is 10 to the 16th Gauss, which is larger than 10 to the 15th. That's the typical field which sits in the dipole component. This is dipole field, and that's probably internal. And most likely it's toroidal. So that means you have a star, you have strong toroidal field, and then you have some dipole component which is weaker, 10 times weaker, And then there is a way for this toroidal field to do these horrible things, like giant flares, for example. And finally, one more unique feature of these objects, also a little bit crazy. Again, normal Newton stars don't do that. Huge dynamic, huge evolution of the spin down rate, this p dot. P dot is not constant. Normally, when you measure p dot, how p is due to spin down of a pulsar, the Crab pulsar, for example, it's a regular spin down. The period becomes longer and longer and longer. You spin down the thing. Here, this rate changes dramatically by a factor of not just by 1%, by a factor of 10 sometimes. So that means that the torque that is applied to the Newton star from its magnetosphere is varying dramatically. And the plausible explanation for that is that the magnetic moment of the star is changing by a factor of like 10. Or let's say, okay, it scales as mu square, maybe by a factor of 3. So it's a star which is alive in the sense that its magnetic moment, its magnetic field is not just frozen and sits there forever like a normal pulsar, but it's evolving on a time scale like months or year, which is much shorter than the age of the star. So unlike the canonical picture of a dead remnant, which is also pulsar is a dead remnant of stellar evolution essentially. Okay, it's got some rotation, it's got some magnetic moment. Yes, there is a discharge which produces bright emission, but nothing is happening in the star itself, not much. Okay, so here the magnetic field of the star is evolving, and we would see it in the evolution of the magnetic moment. You look at it one day, magnetic moment is this way. You look a month later, the magnetic moment points the opposite way. So something is happening inside the star. Okay. Well, another thing that happens is the glitches. Glitches are the jumps in the spin period, which are usually small. You cannot plausibly suddenly change spin period by significant amount because there is a lot of course, moment of inertia. It would involve huge energy change. But at the level up to 10 to the minus 6, 10 to the minus 5, you have this delta p over p is jumping sometimes in pulses. These are called glitches. For example, the Crab pulsar is observed to glitch. Vila pulsar, another famous pulsar, also actually produces even stronger glitches. And they have the characteristic behavior when p suddenly, the star spins up, interestingly, during the glitch. So it's rotating, and then boom, period suddenly becomes shorter. So it spins up and then recovers back. Now, that's an interesting topic by itself. It's related to fascinating physics dealing with superfluidity of the Newton star material. The fact that the neutron fluid rotates somewhat differently, because it is a superfluid, it rotates somewhat differently from the, let's say, crust of the star, which is normal material, and the rest of the star. The reason why it happens, well, I'll spend a minute on that because it's a pretty amazing phenomenon. Essentially, we deal with the huge nucleus, and superfluidity is studied in nuclei in physics, right? We know that nuclei is superfluid. So here, a gigantic nucleus with 10 to the 57 nucleons in the system, packed closely together and held together by gravity. So it's unlike normal nucleus, it's tremendously compressed at a huge pressure by gravity, but still it's superfluid. So neutrons pair, this Cooper pairing, and as a result, rotation is quantized into vortices. Now, these vortices, let's say in the lower crust, these vortices feel the presence of crustal nuclei around them, because rotation of neutrons, there is strong interaction force, which depends on the relative velocity. And so rotating neutrons feel the presence of lattice. And so these vortices tend to pin on the lattice. Boom, like little magnets. They interact with the lattice sites and they get pinned to it. Now, if you think of the effect that comes from that interaction, is that as the star spins down, because there is this magnetospheric torque applied to it, so it is spun down gradually. So the crust begins to rotate slower and slower, and the core as well. The only way for neutron superfluid to rotate slower and slower is to move these vortices away from the axis because each vortex is basically a single line, it's a quantum of rotation. If you fix the position of the vortices, you fix the profile of angular velocity of the neutron of the superfluid. So if these vortices are stuck to the crust, the neutron superfluid cannot possibly change its angular momentum at all. So even though the crust spins down, the neutron fluid does not spin down, as long as the vortices remain pinned. There is, however, a force that tries to unpin them. That's the Magnus force. Do you know what's Magnus force in hydrodynamics? That's what soccer player use. Anyway, for those people who just watched football games, if there is if there is a gas flow past a cylinder, if it's a cylinder, let's say, or a ball is moving this way through a gas, and there is some circulation of air, there will be a force that pushes this cylinder in the perpendicular direction. That's called Magnus force. So you need rotation and motion. And so vortex is basically you have rotation, and you have neutron superfluid that is rotating differently than the vortices. Vortices are pinned to the crust, okay? And so they rotate together with the crust. But the neutron superfluid itself is rotating faster. And so they go past the vortices. And therefore vortices experience this Magnus force. Right? Yeah?
Is there an associated radiation with this force?
No, radiation, it's all hidden inside the star. I'm talking about the inner crust where you have free neutrons. So its density is higher than the neutron break density, which is 4 times 10 to the 11th gram per centimeter cube. So that's where you form this sea of free neutrons. They pair, Cooper pairs, they form these pairs, and they become superfluid because of that. So like in an energy spectrum, there appears a gap, and so they basically stop scattering, interacting with each other. They lose any viscosity. And then you have this transition to quantized state where vorticity is quantized. Vortices are stuck in the crust. Vortices are rotating with the crust. The crust spins down, and the vortices begin to rotate somewhat slower than the superfluid. And the superfluid rotation, of course, is determined by the density of vortices. It's a little confusing situation, but that's all what it is. If you think about it, it's interesting. Vortices are not, you can even stop the vortices if the crust stops. But if the vortices are at the same position, the neutron superfluid is going still to rotate very, very fast. And so that means that the superfluid goes past vortices and it applies Magnus force. This Magnus force, just normal classical hydrodynamics, the same Magnus force, tries to push these vortices away from the axis. And in this way, that's the only way for the superfluid to spin down, actually. If there is a lag and it spin down because of the spinning, this Magnus force will grow more and more, and at some point it will become strong enough so it can push vortices away from the axis, and then the superfluid spins down finally. So the way it happens, and it's observed, so the only reason I'm talking about this in such detail, because the fascinating part is that this theoretical picture is confirmed by observations. We do see glitches in pulses in the magnetars too. And they're associated with sudden unpinning events. So the superfluid vortices are pinned, and at some point the Magnus force grows, and at some point they suddenly move. That means that the superfluid is spun down, right, trying to catch up the spin down of the crust. But the angular momentum is conserved. And so the angular momentum lost by the superfluid is passed to the crust and the star itself. And it means that the star spins up. Okay, that's the spin-up glitch that we see. Yeah.
So the vortices themselves are also made of the neutron.
Vortices are mathematical, if you like, lines. Single lines. It's basically, superfluid does not tolerate vorticity. So vorticity is 0 everywhere except delta function, if you like, the singular line. So it's a line and there is circulation around that line. The circulation is constant. So if I look from above, so that would be the axis of rotation of the star, and there is an array of vortices. I won't be able to plot each of them. There are many of them. And the Magnus force acts this way. Vortex is a rotation of the fluid around it. But of course, each of them does the same thing. And together, when you add up all these individual vortices, together they form this rotation. If you add up this plus this plus this, together they produce this macroscopic rotation. Now, the superfluid rotates faster than the vortices themselves. That's why this relative motion with this vorticity gives you the Magnus force. So at some point, vortex lines will move out, so relocated this way, and that means that you have now less angular momentum in the superfluid. It rotates slower. And this angular momentum is taken up by the crust itself. It spins up, yeah. Yeah.
Oh, sorry. So how exactly are the vortices pinned to the crust here?
Nuclear force. So, yeah, it's you have motion. It's actually not understood. The energy, all you know is the energy scale. You know that nucleons interact, when they move, they interact with the static lattice nucleus. And so it feels the presence of, if there is a vortex next to a nucleus, it feels its presence, and it's not even clear if it's attracted or repelled, but clearly there is some interaction. Let's say it's attractive. And this interaction means that vortices try to, they know about the crust, essentially. They do not move easily through the crust.
So if these vortices are sufficiently pinned to the crust, can they crack the crust if the Magnus force is strong?
No, it's not going to be strong enough. It's a good question, but you can make the estimate. And yeah, obviously there is an exchange in momentum. And this exchange will be particularly interesting when you break the axial symmetry. So you can think of what would happen if you lose axial symmetry. Let's say here in this region, you take and evacuate these vortices, like let them move, unpin them. One way to do that, for example, that's what's happening in magnetars, we think, is that you can heat up this region. When it becomes hotter, just thermally, vortices tend to get unpinned easier. And so then the Magnus force wins and pushes them out of this region. And that means that the flow of superfluid now becomes more complicated. It's not axially symmetric. And in this process, there is an exchange of angular momentum between the crust, and so there is some dynamics there. You're right, but I don't think you can break it this way. You can absorb the momentum. So these glitches are seen in magnetars, and they're particularly strong and frequent. And sometimes they are associated with radiative events. I said that you do not see easily what happens inside the crust. Obviously, it's buried, right? It's high density, it's hundreds of meters depth, so you don't see emission directly from there. But something that is happening and accompanying these kind of events translates to the magnetosphere. And so we do see some magnetospheric phenomena. We do see the change in X-rays, in X-ray luminosity during these, associated with these glitches also. I'm telling you kind of what is the phenomenology, but not much of this is understood yet. So I'm just summarizing what we know from observations, and we have some ideas, but it's not really worked out. Well, we are actually finishing a paper on that topic. So it's very, there are a few people who try to solve this problem. It's a complicated, well, for example, this pinning and unpinning stuff is not really clear. It's not, if one question you would ask, for example, what's the rate of thermal creep of vortices? At finite temperature, you would expect that these vortices would gradually try to jump from one lattice nucleus to another. And this thermal driven creep rate is not, no one knows how to calculate it really. I mean, there are a few papers which claim opposite give completely different results. And I suspect that none of them is right. But so it's a complicated topic. But obviously something like that is happening there. We observe this. Okay, so one more piece of data. This is the spectrum. I told you that the spectrum of these objects is not black body. Right? What you see here is the X-ray spectrum of one magnetar with this, it's an anomalous X-ray pulsar for U01, 42 plus 61, whatever the number is. By the way, the initial classification, the difference between soft gamma repeaters and anomalous X-ray pulses is now completely blurred. There is no real difference because before the difference was that soft gamma repeaters bursts, okay, and anomalous X-ray pulses just produce persistent luminosity with high luminosity, similar period, but no bursting. Now, for many years by now, like 15 years, we know that anomalous X-ray pulses also burst. So actually, there is no real difference between SGRs and AXPs. It's the same class, magnetars. And so this is a spectrum of one AXP, which has two components, as you can see nicely here. So one is quasi-blackbody component, which peaks at 1 keV. Okay, so if it's a thermal spectrum, the blackbody emission has peak at close to 3 kT. So 1 keV peak means temperature something like 0.3 keV. I think 0.5 more exact, 0.4 in this case. So it's soft X-rays. Okay, very nice spectrum. It's not exactly blackbody, really. I cannot jump to show this, but you see the slope. It's not quite exponential. It's not the Wien spectrum. There's no exponential cutoff. It's a soft parallel. The discovery that happened also about 15 years ago, completely unexpected. For years, people thought, like for 30 years, that that's it. You have just soft X-ray component, that's it. Then it turned out that even more energy is actually emitted in hard X-rays in a separate component, which the spectrum turns up and goes to their upper limits, but for other objects, we can actually see that it continues toward 1 MeV, and it's clear that there is a lot of emission coming from in that hard X-ray band, above 100 keV. So what it tells you immediately is a simple thing, that a lot of energy is emitted from the magnetosphere of the star, not from the surface, okay? The keV temperature is what you expect. How you would estimate keV? Okay, you take the luminosity that you observe, 10 to the 35 ergs per second. You know the area of the Newton star surface, 10 to the 13 centimeters squared. You divide them, you get sigma t to the fourth. The flux, you find temperature, the black body temperature. And it's going to be 0.4 keV. So it's the right temperature. So it is surface emission. Maybe it's modified, the Ceph component. Maybe it was modified, certainly. It's not quite Planck. It was modified in detail by some radiative transfer effects, including scattering in the magnetosphere. But the emission at 100 keV certainly is not coming from the surface. It's not thermal emission. So it has to be coming from it's not thermal emission coming from the exterior of the star, from the magnetosphere. So what it tells you that not only occasional flares can produce this bright magnetospheric emission. So many of these magnetars are persistently bright. They have persistent magnetospheric activity, like the sun. If you like, they have a corona. But unlike the sun, the coronal luminosity is exceeding the photospheric surface luminosity. For the sun, it's like 1/1,000,000th something, okay? So it's a tiny, all these flares that we see in the sun they have tiny energy budget. They're very impressive, of course. They produce, the impact the Earth, coronal mass ejections are impressive, but in terms of total energy, they are nothing compared to the light that goes steadily from the sun, from the solar surface. Here is the other way around. Most of the emission actually comes from the exterior rather than from the surface. It's 3:22. Okay, I'll mention one more thing, and I guess I should stop. Right. Just one plot that can summarizes also the temperatures Just highlighting, remember I showed you the cooling curve of neutron stars. And so some of the data points here are just normal neutron stars. There are different subclasses. The red symbols are shown here. And this is the thermal luminosity. This is the soft component, soft X-ray component. It comes from the surface. These red points obviously are above the cooling curve. So that means that the magnetars are much hotter than a normal passively cooling neutron star would be. What it means in turn that there is an energy source. So if it's not as cold as it should be at its age, compared to other passively cooled neutron stars, that means that something is heating it. So inside the star there is dissipation. It's not only magnetospheric activity, but probably also inside the star somehow this magnetic energy is converted into heat, and then this heat flows to the surface and produces brighter thermal emission. And exactly how this happens, I will start to talk next time, and then I think that's the, yeah, I'll stop here. It's a good moment to stop. All right? So now you can ask some questions maybe about this stuff. You have to survive another lecture, by the way. Yeah.
Have some dynamo processes also operating inside the neutron star to throw that field up to like 10 to the 6.
Yes, that's exactly right. So you need dynamo, most likely dynamo, to unless you have an anomalously strongly magnetized progenitor. So if you want to bring up fields to 10 to the 16 Gauss, it's a bit hard to do but just by simple collapse, because this BR square conservation is not really giving you the strong fields. But if you have dynamo acting, then you can bring the field, in principle, up to a good fraction of equipartition. And that could be even 10 to the 17th Gauss. So 10 to the 16th is not a problem. And that's obviously what is happening in this case. That's the only plausible explanation, this really strong magnetic fields. Yeah?
Can we talk about angular momentum exchange between the crust and the core, all these vortex spinning and so on, in terms of some friction, characteristic timescales, and what are these?
What are the timescales? Well, fundamentally, this is strong interaction, right? So when the vortex is moving, it has to pass, the momentum of the superfluid has to be passed to the crust through strong interactions.
But that's extreme, isn't it?
It's this extremely short time scale. You cannot possibly resolve it. And by the way, of course, glitches are not resolved normally. These smooth variations in spin-down torque, they resolve nicely, as I showed. But glitches, they occur like that. They're never resolved.
But it's a part of a more gradual process, like alignment and angular momentum exchange between the core.
No, the momentum of the core and the crust, they are coupled.
The superfluid part, right?
They are coupled. The star is coupled, well coupled. I don't think you can have differential rotation between the core and crust, I think, especially when you have, in these objects, when you have magnetic fields, because the magnetic fields penetrate, they provide coupling, essentially. Magnetic field lines coming through the interface between the crust and the core. So the crust is like 1 kilometer thick. The core is about 10 kilometers in radius, and there are magnetic field lines threading the crust and the core. So this system is all coupled. One characteristic timescale is the so-called Alphen timescale. So for the core, it would be the right one. So if anything happens in the core, I'll talk about probably next time about this. If you perturb the core, then the characteristic dynamic time, it's like liquid. Core is liquid. It's a liquid neutron-dominated core. It behaves like medium with strings. So you can think of magnetic field lines as strings. If you perturb it, you launch Alphen waves. These are the shear waves that propagate along the magnetic field lines. So the characteristic timescale for the core to conduct these modes would be the Alphen crossing time.
And it's also, of course, much shorter than all the evolution timescales.
That would be a fraction of a second. So it's much shorter than the period of rotation.
So we more or less may talk about neutron stars as rigid bodies with some moments of inertia.
Oh, next time I won't talk about them as rigid bodies. That's the main point of my talk, that magnetars are not rigid. Yes, so it's a good point, and yes, it's exactly right. Magnetars are not rigid at all. They are constantly broken. I mean, they try to be rigid in some parts, but they don't have this easy life. It's like they're star quakes, if you like, all the time.
Do you think the core of neutron stars in general could contain like different phases of matter, like quark matter?
This I don't. Yeah, that comes to the unknown equation of state. So at high densities, when you go beyond 4 or 5 times 10 to the 14 grams per centimeter cube, the equation of state is not really understood. That could be the range of options is tremendous. I showed the the effect of different equations of state for the mass radius relation, the most important observable characteristic of a neutron star. Huge uncertainties. It could be soft, meaning like pressure for the same density is much lower compared to stiff equation of states when at the same density you have higher pressure. So stiff equations of states tend to give you bigger stars. And that's why you saw the difference between radii for different equations of states. But it's unknown, so I don't want to review that even, because there would be no conclusion there, I think, except for some observational constraints that I mentioned.